Hello everyone, welcome back to my YouTube channel. In today's video, I would like to share with you a real field job related to the installation and troubleshooting of a Rosemount flow transmitter, Model 3051S. This is a very common transmitter used in industrial plants, especially in oil and gas, power plants, and process industries. So I believe this topic will be useful for technicians, engineers, and anyone working with instrumentation systems. Now, let's start with the installation process. First of all, we installed the Rosemount 3051S flow transmitter at the designated location according to the PNID and installation drawing. The impulse lines were already installed properly, and we made sure that the high-pressure and low-pressure sides were connected correctly. The transmitter was mounted firmly, and the orientation was checked to ensure correct measurement and easy access for maintenance. After the mechanical installation was completed, we moved on to the electrical wiring. The transmitter uses a standard 420 mA loop, and it is also HART-enabled. We connected the signal cable to the terminal block inside the transmitter housing, making sure the polarity was correct. The cable shielding was grounded properly to avoid noise or interference. Once the wiring was completed, we proceeded to power up the loop. The power supply comes from the AI card in the control system, and the nominal supply voltage should be 24 VDC. At this stage, everything looked normal from an installation point of view. So the next step was to perform configuration and verification using a HART communicator. However, this is where the issue started. We connected the HART communicator across the loop, following standard practice, but unfortunately, the communicator could not establish communication with the transmitter. It kept showing a connection failure or no device found. At first, we suspected a simple connection issue. So we rechecked the communicator leads, ensured proper contact, and tried again. But the result was the same, no HART communication. Then we started a step-by-step troubleshooting process. The first thing we checked was the power supply voltage. Using a multimeter, we measured the voltage at the transmitter terminals. The reading was 24 VDC, which is exactly what we expected. So we could confirm that the transmitter was receiving sufficient power from the AI card. Next, we checked the signal cable. We verified cable continuity, checked for any broken wires, loose terminals, or short circuits. We also inspected the cable routing to ensure there was no physical damage. All cable checks came back normal, and everything looked fine. After that, we considered the loop resistance. As you may know, HART communication requires a minimum loop resistance, typically around 250 ohms, to allow the digital signal to ride on top of the 420 mA current. In our case, based on the system design and the AI card specification, the loop resistance should have been sufficient. Despite all these checks, the HART communicator still could not connect. At this point, we started to suspect that the problem might not be on the field side, so our attention turned to the AI card itself. Even though the AI card was supplying 24 VDC, it is still possible that the internal HART circuitry of the card is faulty, or that the card does not properly support HART communication due to configuration issues or hardware problems. In some cases, an AI card can provide correct loop power and still block or distort the HART signal. This can be caused by damaged components, incorrect filtering, or even incorrect channel configuration in the control system. So the next planned action is to perform further checks on the AI card. This may include testing the transmitter on a different AI channel, using an external power supply, or connecting the HART communicator directly with a test resistor to confirm that the transmitter itself is healthy. To summarize this job, we successfully installed the Rosemount 3051S flow transmitter. The wiring and power supply were confirmed to be correct, with 24 VDC present at the transmitter. The signal cable was checked and found to be in good condition. However, HART communication could not be established. And based on our troubleshooting so far, the AI card is suspected to be the root cause of the issue. This kind of situation is actually quite common in real industrial environments, and it shows why systematic troubleshooting is so important. Instead of replacing devices randomly, we need to verify each part of the loop step by step. Thank you very much for watching this video. I hope this real case study helps you in your daily work with transmitters and control systems. If you find this video useful, please like, share, and subscribe to the channel. And if you have experienced similar issues with HART communication, Feel free to leave a comment below. Now, let's take a deeper look at some possible reasons why HART communication cannot be established, even when the transmitter is powered and the wiring appears normal. First, one of the most common causes is insufficient loop resistance. As we know, HART communication works by superimposing a digital signal on top of the 420 mA analog signal. For this digital signal to be detected, the loop must have enough resistance, typically at least 250 ohms. If the total loop resistance is too low, the HART signal will be heavily attenuated, and the communicator will not be able to communicate with the device. This can happen especially when the AI card has very low internal resistance and no external resistor is installed. Second, the issue can be related to the AI card HART capability itself. Not all AI cards fully support HART, and even among HART-capable cards, the HART circuitry may be damaged or disabled. In some cases, the card supplies correct 24 VDC loop power, but its internal filters block the high-frequency HART signal. This situation can be misleading because everything appears normal from a power and current perspective, but digital communication is still impossible. Another possible cause is incorrect grounding or shielding. If the signal cable shield is grounded at multiple points, or if there is electrical noise nearby, the HART signal can be distorted. Strong electromagnetic interference from motors, variable frequency drives, or high-voltage cables can also disrupt communication. Even though HART is quite robust, excessive noise can still prevent the communicator from detecting the signal properly. The connection point of the HART communicator is also critical. If the communicator is connected in the wrong location, such as across terminals with additional electronic components in between, the HART signal may not pass through. Best practice is to connect the communicator directly across the transmitter terminals or across a known load resistor in the loop. Another factor to consider is device configuration or firmware compatibility. If the HART communicator does not have the correct device description or DD file for the Rosemount 3051S, it may fail to recognize the device even though communication is physically possible. In such cases, the communicator may display generic messages or fail to connect entirely. Firmware mismatches between the transmitter and the communicator can also cause similar issues. We should also consider the possibility of loop current being outside the normal operating range. If the loop current is fixed at a value such as 4 mA due to a fault, or if the loop is saturated at 20 mA, HART communication may become unstable or impossible. This can occur if the transmitter is in alarm mode, simulation mode, or if there is a configuration error. In addition, incorrect polarity, although less common, can still be a factor. Some transmitters can tolerate reversed polarity for power, but HART communication may not function correctly in such conditions. Therefore, polarity should always be verified during troubleshooting. Finally, we cannot completely rule out a faulty transmitter. Although rare, internal electronic failures can prevent the HART modem inside the transmitter from working properly, even if the device still outputs a 420 mA signal. Testing the transmitter on a bench setup with a known good power supply and resistor is often the fastest way to confirm whether the transmitter itself is healthy. By understanding all these possible causes, we can troubleshoot HART communication issues more effectively and avoid unnecessary replacement of equipment. A systematic approach not only saves time, but also helps maintain reliability and confidence in the instrumentation system.